This lesson is introducing the 6 trigonometric functions. And before I start talking about these functions abstractly, what I would like to do is to show you a video clip that I've recorded demonstrating to you what these things are more concretely. And in that respect, let me go ahead and start that video and let you see that. Hello and welcome back. Congratulations for making it this far. I am going to look at another aspect of triangles that is interesting. And last time we looked at how triangles were rigid objects and they were inherently stronger objects simply because of their shape than squares or other types of objects that are not rigid. Now, what I want to look at today is the side lengths of triangles and how that relates to the angles opposite those sides. I have with me 4 different triangles and differing sizes. I'm going to start with the largest triangle, and what I'm going to do is I'm going to use this device here to measure the angles within the triangle, and then I'm going to use my tape measure in order to measure the side lengths. But to keep things nice and simple, I'm going to use centimeters because that's a whole lot easier than inches and feet. Now, let's get started with finding angle measures. So I'm going to use my angle finding gauge here. And on the largest triangle, the small angle there is about 25 degrees. So I'm going to make this the red triangle, and I'm going to label this triangle, this angle right here, as 25 degrees. And I'm going to call it theta. We often call our angles that we work with in the triangle theta, and that just basically tells us what our observed angle is. That's the angle that we're directly looking at, because there's multiple angles involved. This one over here is our right triangle. And everything we do for the first couple of chapters is going to be dependent solely on right triangles. So one of these angles is going to have to be 90 degrees. The remaining angles, what's interesting is that they have to add up to 180 degrees total. And that's the property of all triangles. If one of those is 90, the remaining 2 have to add up to the leftover 90. Because if I have 180 total, this makes up 90. That leaves 90 between the 2 of these. If I know one of those angles is 25, the other one, if you grab your calculator or you just do it in your head, whichever you prefer, is going to be 65 degrees. So this angle measure up here is going to be 65 degrees. And I can show that by getting out the angle measurer and find out for sure if that's the case. And it turns out that's pretty accurate. It looks at about 64 maybe, but I probably didn't cut these with, complete precision. So it works out pretty well. In fact, the reason that it's not 65 is probably more that the right angle isn't actually 90 degrees. When I cut it, it probably cut to like 89 or something close to it. Who knows? But in theory, that's the way it should be. Now, we know the angle measures. Let's look at the ratio of sides. Let's look at the side lengths. So the bottom is about 70 centimeters exactly. So I'm just going to label the bottom as 70 centimeters. The top, or the other side here, it looks like it is about 32 and a half. And then the longest side, the hypotenuse that is, and I measure it out, it comes out to about 77.3. Now, of all of those sides, get it to stand up here, see if that's possible. Not bad. Of all of those sides, there is something special in the relationship between the sides. So for instance, what I'm going to do is I'm going to take the ratio of two sides, meaning all I'm going to do is divide. So I'm going to take the ratio of 32.5 to 70. So 32.5 divided by 70. So 32.5 divided by 70 is 0.46, okay? This is the 32.5 is the side opposite my observed angle, and the 70 is the side that is adjacent to my observed angle. Now I'm going to do, so this is the opposite side compared to the adjacent side. Now I'm going to do the opposite side over the length of the hypotenuse. The opposite side over the length of the hypotenuse. So the opposite side is 32.5. The length of the hypotenuse is 77.3. When I divide those, I get about 0.42. Lastly, I'm going to do the opposite side divided by the adjacent side. So, I'm sorry, I completely messed up there. I'm going to do the adjacent side over the hypotenuse. That's what I want. Don't know why I can't write right now. All right, adjacent side over the hypotenuse. So the adjacent side, that's length 70. The hypotenuse is 77.3. So I'm going to do 70 divided by 77.3. So 70 divided by 77.3, that gives me about 0.91. Now, I'm going to do the same for all the other triangles, but with the miracle of modern editing, it's going to happen very quickly. So I'm just going to take the next smallest triangle, and I'm going to fill out all of its information with side lengths and angles in green. Okay, I've done all the measurements. So what I've done is taken each of the triangles and simply found the angle measures for each one and the side lengths for each one. The next smallest triangle I have, theta is 25. The side opposite theta is 22 centimeters. The side adjacent is 47.3, and the hypotenuse is 52. And the smallest triangle that I have, again, theta is 25 degrees. The side opposite is 16.3, the adjacent is 35, and the hypotenuse is 38.5. So, obviously different side lengths per triangle, but the angle measures are all the same. So now what I'm going to do is I'm going to find the ratio of sides of all of these and see what happens. So let me speed the camera up again and let's watch. Okay, so I've done all my measuring and I've found the ratio of the individual sides. Now look what's happened. So the opposite over the adjacent for the red triangle, that ratio is 0.46. For the green triangle, that ratio is 0.46. For the blue triangle, that ratio is 0.46. It doesn't matter what the size of the triangle is, it only matters what the angle measure is. That tells you what the ratio of the sides is going to be. Let's look at the opposite over the hypotenuse. For the red triangle, the ratio of those sides was 0.42. For the green triangle, that ratio is 0.42. For the blue triangle, that ratio is 0.42. For the adjacent over the hypotenuse, when we compare those sides, for the red triangle, 0.91. The green triangle, 0.91. For the blue triangle, also 0.91. So it doesn't matter what the size of the triangle is, it just matters the angle measures within the triangle. So these are all called similar triangles because the angle measures within are all the same. That makes them similar. So in similar triangles, you will always see this relationship. Now, that leads us to the 6 trig functions. We'll explore them in detail in a little bit. But for right now, just know that when we're doing the opposite over the adjacent side, that is a trig function called the tangent. And the tangent of something that is 25 degrees, if you look it up on your calculator, tangent 25, just make sure you're in degree mode, it's 0.466, which basically rounds to 0.47, but that 0.46 to 0.47 difference is really just rounding error, I guarantee you. When I'm measuring to the nearest first decimal, and that's probably not accurate enough. Opposite over the hypotenuse. This is a trig function that we're going to refer to as the sine function. The sine of an angle measure that's 25 degrees, if you look it up in your calculator, is 0.42. Exactly what all of these found. For the adjacent over the hypotenuse, this is, a cosine. So the cosine of an angle measure that is 25 degrees probably shouldn't surprise you if in the calculator you get 0.91 or something extremely close to it. So let's see what happens. Cosine 25 degrees, it is 0.91. So these values of sine, cosine, and tangent that you're going to learn about through this class, just keep in mind at the very center of those, it is all about the relationships of the ratios of the side lengths and similar triangles. Now I have one other triangle that I measured in purple. Only difference is theta here is 40 degrees. That's my observed angle. So for this triangle, let me get the ratio of sides for each one. Let's see if they're the same or if they're different. So for the purple triangle, I'll speed things up again. Okay, so as you notice, the opposite side divided by the adjacent side in the purple triangle is now different. I get 0.83. I no longer am getting 0.46 because I'm not dealing with similar triangles. They don't have the same angle measures within. I'm dealing with an observed angle of 40 degrees rather than 25 degrees in these right triangles. That changes the ratio of sides. But it shouldn't surprise you that if you hit tangent to 40 degrees, you get basically 0.839, which is 8.4, which is close, okay? And then the next ratio of sides, this is the opposite over the hypotenuse, the sine function. 29.1 over 45.7 gives you 0.64, which is different from the 0.42 we were getting. So when you have similar triangles, the ratio of sides are always the same in the triangles, regardless of the size of the triangle. When you have triangles that have different angle measures within, that no longer is the case. When it comes to the trigonometric functions, as described in the video, there always is some sort of observed angle, which is usually referred to as theta, so that's what I have here. And when you have that observed angle, on the other side of your triangle, you have your opposite side. And based off of that observed angle, you have the side that's adjacent to you. So that's the side that it's resting on. And then you have, because you have a right triangle, and this little square in the corner indicates that it's a right triangle, then opposite your right triangle is your hypotenuse. So basically, in any triangle, any right triangle, you have a hypotenuse, which is probably the more important side. It's the easiest to identify because it's always going to be the longest side. And opposite and adjacent sides, you just have to determine those based off of what your observed angle is. Because if I made this my observed angle, then now, tell you what, let me do it in a different color. So if I make that my observed angle, this is now my opposite side of that observed angle. This is now the adjacent side to that observed angle. But this is still the hypotenuse. So the hypotenuse is always the longest side and always opposite your right angle. Now, let's go back to just this angle measure theta. And some things that I want to just reinforce that were stated in the video, but just get them written down. The definitions of our trig functions. The most important trig functions are sine, cosine, and tangent. And we also have three others. We have cosecant, secant, and cotangent. Before we get into those, let's talk about the main three: sine, cosine, and tangent. So sine of your observed angle. This is just the ratio of the sides opposite over hypotenuse. So it's just the ratio, the sine is just the ratio of sides of the triangle for that given angle measure. Cosine is defined as the adjacent side divided by the hypotenuse. So that's why it's so important to be able to determine what the opposite side of your observed angle is and what the adjacent side is and what the hypotenuse of the right triangle is. That's how you define these trig functions. Tangent is defined as opposite over adjacent. The remaining trig functions don't actually introduce anything new other ratios. They're just more convenience functions. There's times where when you're solving something based off of the opposite side and the hypotenuse, it's more convenient to use the hypotenuse over the opposite side. That's your cosecant function. It's essentially the inverse of your sine. Same thing for secant. It's related to cosine. It's just the hypotenuse in the numerator and the adjacent side in the denominator. And then cotangent is similar. It is the adjacent side divided by the opposite side. Now, one way to remember all this, as silly as it may sound, my trig teacher told me to always remember SOHCAHTOA. And again, as silly as it may sound, I have remembered it ever since then. She told me it was that SOHCAHTOA is the princess of the trigonometry tribe, which is kind of funny still to this day. But it's extremely important because it kind of helps you remember all these different pieces of information. So the way it helps you remember this stuff. So S stands for sine, and sine is defined as the opposite side over the hypotenuse, so O over H. And then C stands for cosine, A and H stand for adjacent and hypotenuse. T stands for tangent, O and A are standing for opposite and adjacent. So it just tells you how to remember, an easy way of remembering the way these functions are defined. Now, we're going to explore this a whole lot more when we get into solving some right triangles. For now, we're going to take a little bit of a detour, and we're going to look at trigonometric functions based off of their definition and standard position. So we let xy be a point in the xy plane that defines the terminal side of an angle in standard position, and r be the distance of that point to the origin. The distances x and y can be thought, that should be a t there, thought of as the legs of a right triangle with hypotenuse r. Using this setup, you can define the 6 trigonometric functions as sine of theta equals y over r, and theta being in parentheses here is not necessary. It's sometimes if you're inputting an angle measure, sometimes you put it in parentheses. It can be in parentheses or it cannot be in parentheses. It doesn't make a difference. But we can define sine of theta as y over r, cosine theta as x over r, and tangent of theta as y over x. Now, before we go into the other trig functions, let's explore why this is the case. So here's a coordinate axes, and I'm calling this my x-axis and this my y-axis. I'm just going to make some random angle measure here. So if I have a point on this angle measure, and I'll label it xy, what that means is that in order to get to this point right here, starting from the origin, I have to travel over some distance x. Then I have to travel up some distance y. If you'll notice, x and y, of course, are going to make a right angle with each other. And so I've basically created a right triangle. The only thing that's not known about this triangle is the distance r, but that just happens to be the distance of this point from the origin. So I could say r is equal to the square root of, x minus 0 squared. Oops, I didn't mean to put x squared. Let me try that again. X minus 0 squared plus y minus 0 squared. So that calculates the different distance between 2 points. Or it just simplifies to the square root of x squared plus y squared. Now, if I think of this as my observed angle, and I'll label it theta, then basically I can say, sine theta is equal to what we just learned from SOHCAHTOA is the opposite side over the hypotenuse. Well, the opposite side is right here. It's length y. The hypotenuse is right here. I spelled that really terribly. It's a terrible y. Oh, that eraser's so big, it erases everything. which means I have y over r. Exactly what I stated up here. So sine of theta is the opposite of that angle measure theta divided by the distance from the origin to the point. So it's just another way of defining the exact same situation. Cosine is going to be, so katoa, so it's going to be the adjacent side over the hypotenuse. So this is my adjacent side, which is length x. So it's x divided by r. Exactly what we stated right there. And then finally, tangent is, so SOHCAHTOA, so opposite over adjacent, that is y over x. Exactly what's stated up here. Now there is a little bit more information where it says x cannot equal 0. So there are situations where tangent is undefined, and that's where x just happens to be 0. So we have to kind of watch out for that. The remaining trig functions, cosecant, secant, and cotangent, these are just the inverses of the remaining of the first three. So if you'll notice, cosecant is defined as r over y. So what we said is the hypotenuse divided by the opposite side, and so forth. So that's how we define our trig functions in standard position. Let's see how that's used. So let's evaluate the 6 trigonometric functions for the angle defined by the point 815. All right, so let's say, for instance, this is the point 815, and this is clearly not drawn to scale. So let's see how this works. So the distance y is my y coordinate. So the length of this, or the height of this triangle, is 15. The width of this triangle is my x coordinate, which is 8. I have a right triangle. I'm going to call this my observed angle, theta. Yeah, let me write that better. And then r. Well, we have to calculate r in this case. So r is going to be the square root of 8 squared plus 15 squared. 8 squared is 64. 15 squared, grab your calculator if you're not sure. That's fine, it's 225. These add up to 289. And this, if you take the square root of, you'll find is exactly 17. So this distance this way is 17 units. When I calculate sine of this angle measure, then it's the opposite side over the hypotenuse. The opposite side is 15, the hypotenuse is 17. And I could divide these two and turn this into a decimal approximation. That would be easy enough to do on the calculator. I'm not going to, because a lot of times it's more convenient to have the exact answer when you're dealing with trigonometry. So 15 divided by 17 is an exact answer. If you actually got a decimal on the calculator, that would be an approximation. So a lot of times you'll be asked in trig to answer using exact answers or answer using approximations, and that's the difference. So the approximations involve decimals, exact answers involve fractions. Cosine theta, this is going to be the adjacent side over the hypotenuse, so 8 over 17. And tangent theta is the opposite side over the adjacent side, so 15 over 8. Now the remaining trig functions, we have cosecant, we have secant, and cotangent. These are all just the inverses of what we've just found. So we don't really need to go through and calculate these at this point. Cosecant is going to be 17 over 15. Secant is 17 over 8. And cotangent is 8 over 15. Now, this is a method of defining your trig functions based off of a point in the plane. And if you'll notice, we don't actually know what the angle measure theta is. It could be calculated, but we're not going to calculate it at this point. So this is just defining trig functions off of some point in the plane. What I would like to show you now is a little applet to kind of demonstrate how this would work in general for any points. Give you a feel for, the differences between exact answers and approximations, for instance. So let me pull that up. Okay, so for any point that I define here in this plane, P, I can move that point around and show you what the values of the different trigonometric functions are. I have the definitions of the trigonometric functions here, and in this little dashboard, those calculated values. So for any point P, these will change based off of where I move my point to. So let's move my point here. So if you'll notice, theta is my observed angle. This would be my opposite side of theta, and this is my adjacent. And then, of course, this is my hypotenuse right along here. So sine is defined as the opposite side, which is 8, divided by the hypotenuse, which in this case is calculated as the square root of 80. Now, this isn't a reduced answer. So like, for instance, if I have sine theta equals 8 over the square root of 80. So it's not a reduced answer because a couple of things can happen. So first off, you can't have square roots in the denominators of your fractions, so that would need to be rationalized. And so to rationalize it, I'd multiply top and bottom by the square root of 80, over itself. Also, the square root of 80 can be reduced. So you have to have these radicals reduced and the fractions rationalized. So to start off, like here, this would be, so for 80, 4 is a perfect square and a multiplier of 80. So 80 divided by 4 would be 20. But 20 also has a factor of 4 in it. So this could actually be written as 16 times 5, it looks like. The square root of 16 is 4, so I can pull that out. 4 goes into 8 2 times, so this would be 2 over the square root of 5. If I multiply this by the square root of 5 over itself, that rationalizes the denominator and gives me the simplest answer. So the reason I'm pointing this out is because I want you to understand that these problems in the homework that ask for exact answers for calculating trig functions by points, these are not your answers. They're helping you along the way to kind of give you an understanding of what's happening, but you're going to have to do some reducing. So I'm trying not to give you a tool that will just give you answers to homework problems. All right, so that being said, let me get rid of this. So I can move this point around and even into different quadrants. Now, if you'll notice, if I'm in quadrant 2, the x direction here is negative, so it's negative 8. And if you come down here, that's part of, these functions. So cosine is the adjacent over the hypotenuse, so it's negative 8 over square root of 113. So these functions, these trig functions, can be positive and they can be negative as well. So that's important to understand. If you continue on around, you can get different, different values. Oops, I was supposed to stay there. The 6 I was trying to move up. All right, so in quadrant 3, both the x and the y directions are negative, so you could have differing values there. If you'll notice, I have tangent of theta is now defined as -7 over -6, which, for this kind of angle right here, this is my opposite and that's my adjacent, so that's how it's defining it. Obviously, the answer there isn't -7 over -6. It would be 7/6. You would reduce that to a positive answer. But this demonstration, it'll kind of work for points all the way around. You can see actually what the angle measure is itself. It doesn't place that angle measure in right here because, like I said, I'm trying to show you trig functions defined by points using that SOHCAHTOA rather than defining it by angle measures, which we'll do later. You can also click this button that says to show approximations. And if you show approximations, then everything kind of changes to decimal format. So if you'll notice, my R value, the distance from the point to the origin, is now in decimals. And if you are looking for tangent, perhaps, so if this is my angle, opposite over adjacent would be -8 over 7. Well, if you get your calculator out and do -8 divided by 7, you should get this number right here, -1.1429. So it's now giving you approximations rather than exact answers. So that can happen for any point in the plane. And I just wanted to show you this because it is doing what you did in the last example, but just kind of in general, you can do it for any point. How this works. But let's recall from algebra. In the standard coordinate plane, you have 4 quadrants. Quadrant 1 is where x is greater than 0 and y is greater than 0. Quadrant 2 is where x is less than 0 and y is greater than 0. Quadrant 3, x is less than 0 and y is less than 0. In quadrant 4, x is greater than 0 and y is less than 0. And if you're wondering how I'm deciding this, it just comes down to, what would a point look like in this region? So let's choose a point. So the coordinates here could be something like 5 on the x, but look, I'm in the negative y, so this might be like -4. So the coordinates here would be 5, -4. So x is greater than 0 and y is less than 0. So you can do that for any 4 quadrants and you can see how that works. Now, what does that mean in terms of trig functions? Well, in terms of trig functions, in quadrant 1, all of your trig functions are positive. So sine is defined as y over r. So r is always positive. That's one thing I should note. When you're defining r, r is equal to the square root of x squared plus y squared. No matter what you put in for x or y, when you square them, they become positive numbers. So r is always positive. So keep that in mind. So for sine being defined as y over r, if y is positive and r is positive, then sine is positive. If cosine being defined as x over r, and both of those numbers are positive, then cosine of, let me write it as thetas, of all angle measures in here are positive. In addition, tangents are all positive. So Cosecant, secant, cotangents are just the inverse of these. All of your trig functions are positive in quadrant 1. In quadrant 2, the y values are positive, but the x values are negative. So any trig function depending on x is going to be negative. So sine is positive. So sine of theta and cosecant theta, those are going to be positive. Cosine depends upon x, and tangent depends upon x. Those are all going to be negative. In quadrant 3, both x and y are negative. So that means sine and cosine are going to both be negative. But tangent, which is y divided by x, when you take a negative divided by a negative, the result is positive. So tangent and cotangent are positive in quadrant 3. In quadrant 4, x is positive, y is negative, so now cosine and secant are positive in quadrant 4. And there's a nice way of remembering these. It's a mnemonic. All students take calculus. So what that means is all trig functions are positive in quadrant 1. Trig functions depending upon sine are positive in quadrant 2, so sine and cosecant. Trig function depending upon tangent are positive in quadrant 3, and cosine in quadrant 4. So if you recall that, that will tell you. So if you keep that in mind, that'll help you remember which trig functions are positive where. That's going to become really important later on in the class. All right, now let's talk about the ranges of trig functions. So when it comes to defining sine and cosine, if you have a right triangle and an observed angle theta, and this would be my opposite side, this would be my adjacent side, and this would be my hypotenuse. The hypotenuse is always the longest side. So when I define sine of theta, I'm taking the opposite side divided by the hypotenuse. The opposite side is always shorter, and the hypotenuse is always longer. They might be equal. It's entirely possible that they're equal, but this is more likely. In that case, when you take a smaller number divided by a larger number, you always get something that's less than 1. Same thing goes for cosine. So sine and cosine, the only numbers that you can get out for sine and cosine are between the values -1 and +1. We saw how the sine and cosine could be negative depending on the quadrant. Secant and cosecant, if you take the inverse of those, then you're taking the hypotenuse, which is always longer than the opposite or the adjacent. So you're always going to get something larger than 1. So this is in the range from -∞ to -1, and then 1 to infinity. And tangent, well, tangent you could get any real numbers, just depending on the side ratios. So their range is all real numbers. Okay, so the next thing that I want to show you about triangles is what happens with the trigonometric functions in regards to similar triangles. Now, the setup that I have here, you may not notice it as a similar as two different triangles, but it definitely is. And I'm going to show you what I mean here. Okay, so for instance, I have one triangle that is all the way around, all the way out to point P and back. So that's one triangle. The other triangle, which I'll draw in red, is a smaller triangle right there, defined, oh, I'm sorry, this is actually point P here, and this is point P prime, but the prime is so small it didn't notice it. Anyhow, so I have two different triangles, and I'm guaranteed that these triangles are similar triangles because they contain the same angles within. Like for instance, the red triangle has a right angle and the blue triangle has a right angle. The shared angle between them, which I'll do in green, is 29 degrees. So if this is 29 degrees, then the angle here in the red triangle is complementary to that, which means that they both add up to 90 degrees. So 90 minus 29 is going to be 61 degrees. Same thing in the blue triangle. This angle up here is also going to be 61 degrees because this angle down here is 29. So that means I have similar triangles. So in similar triangles, the angles within the triangles are the same, but not necessarily the lengths of the triangles. And let's look at what that means. Now, for the triangle that ends at point P, this distance from here all the way up to here, this is the 6.680 that is being measured. All right, and then from here to here, this is 3.203, and then from here over to here, that's the 5.862. So these are the lengths of the sides of that triangle based off of point P. The lengths of the sides of the triangle based off of point P prime starts with the y prime, which is this distance this way. The x prime is actually the distance all the way down to the origin. The way I've drawn it, it looks like it's just, from here over to here, but that's not the case. I'm meaning for it to measure all the way across back to the origin. And similarly for the radius. So this radius is the radius all the way back to the origin, so that variable r. So I have the side lengths of each of these two triangles in question. What I want you to notice is the values of the sine and so this says y over r, so this is the triangle based off of point P, and this is y prime over r prime, so this is the bigger triangle based off of point P prime. Notice how they're basically the same. They're not exactly the same, but whenever you divide, there's a little bit of error involved in your calculation, and that's just what you're seeing here. If I move point P, oops, it's to let me move that point. There we go. It changes the length of y and r and x for the smaller triangle. But notice how the value of sine didn't change. The value of sine is going to be the same no matter what the angle measure is. So if you just watch the different values of sine as I slide this point along, for this angle measure of 29 degrees, the value of sine is always about 0.480. Similarly, cosine is about 0.877 and tangent is 0.547. The only way to get those to change, it's having a difficult time determining what I want to move and what I want to draw. Let's do this. There we go. So if I move point P to a different location, oh, it's all crashed on me. So if I move point P to a different location, that changes the value of sine, cosine, and tangent. But the value of sine for the smaller triangle and the larger triangle always agree. Same for cosine, same for tangent. So what that means is the only value that makes a difference when calculating sine, cosine, and tangent is the angle measure. It doesn't matter the size of the triangle. These ratios will always be the same. If you get out your calculator, and first off, you have to make sure you're in the correct mode. You have to be in degree mode. By default, the calculator's in radian mode. Later on in the class, you'll get to the point where you're probably pulling your hair out trying to decide which mode does it want me to be in, radian or degree. But at this point, it's actually very easy. We're only working with degrees right now, so you just need to be in degree mode. So degree mode, if you're in that, if I type in, say for instance, sine 34, then what that's going to do is it's going to give me value for the ratio of sides of a triangle with a 34-degree angle measure. Now, if you'll notice, my answer here is 0.559. Over here it says 0.562. There's a reason for this. The reason is this angle measure theta is probably not exactly 34. I've just rounded it off to the nearest angle measure, so it's probably like 34.2 or something like that. Who knows? So it's not exactly 34. Second, when I'm calculating that sine, I'm just taking the value y, which has 3 decimal places, divided by the value r, which also has 3 decimal places. And over here, the calculator gives you that accuracy out to 9 decimal places. So the accuracy is just not the same. They're always going to be approximately correct, though. So let's try cosine of 34. So if I just hit the cosine button, then 34, close parentheses, now I get 0.829, which in the app over here, 0.827 is what I have. So this app, I'm not exactly going for accuracy. What I'm going for is principles. I want you to understand that the principle of where these values come from. Because if you understand the principle where these values come from, it makes it a whole lot easier to understand what you're doing with them when you're actually solving for them in a more abstract nature. So feel free to mess around with the app here and your calculator to kind of get a feel for what's happening with these. But let's continue on with the next part of the video. Okay, evaluating trig functions at quadrantal angles. In order to do this, let's start off with theta equals 0 degrees. Now, we've already mentioned what a quadrantal angle is. It's an angle that lies on the axis. So an angle measure of 0 degrees is, along the positive x-axis, which it doesn't really make an angle because the initial side and terminal side would be the same. So it doesn't technically make an angle, but we think of it as doing so. And in thinking of it in that way, we are able to calculate values for sine, cosine, tangent, and so forth. In order to do that, however, we need to know a point that exists on the terminal side. Well, I can find a bunch of points that lie on the terminal side, and it doesn't matter which point I use. Like, for instance, a simple one to use would be 1, 0. But I could use 2, 0, 5, 0, 20, 0. It doesn't really matter. As long as the x is positive and the y is 0, I'm going to land right on the x-axis. So using that, that gives me an x value to work with and a y value to work with. And I can calculate r by doing the square root of x squared plus y squared. So r is 1. So what that means is if I try and calculate the sine of 0 degrees, sine is defined as y over r. So y is 0, r is 1, so that answer is 0. Cosine of 0 degrees, it's x over r, so the x value is 1, and the r value is 1. So 1 divided by 1 is 1. The tangent of 0 degrees, tangent is y over x. So 0 over 1, which is 0. And if you get out the calculator, you can verify these. Just, again, make sure you're still in degree mode. Okay. And if I do sine of 0, the answer is 0, for exactly what I just showed you. Cosine of 0 is 1. Tangent of 0 is 0. The other trig functions, we have cosecant, secant, and cotangent. These are all just the inverses of sine, cosine, and tangent. So basically, if I flip this fraction right here, it becomes 1 over 0, which, that's undefined. Well, that's going to happen sometimes. You're going to have trig functions being undefined at certain values. Sine and cosine will never be undefined, but cosecant, secant, cotangent, and even tangent all can be undefined at some points. Secant of 0, we would flip that fraction 1 over 1. It's 1 over 1 still, which is just 1, so that's fine. Tangent would flip to 1 over 0, which is again undefined. So you have to kind of be aware of this. All right, now I'm not going to evaluate all trig functions at every single angle measure, but I want to give you an idea of how this works. So 90 degrees. Theta equals 90 degrees is this angle right here. So if I draw an initial side and a terminal side, my terminal side lies right here. I just need to know a point that lies on the terminal side in order to do these calculations. So a point to use, 1, 0 would be great. And then R again would be, oops, my bad, 0, 1. Let me fix that. So 90 degrees, 0, 1, because it's 0 on the x, 1 on the y. All right, and let's see, eraser doesn't need to be as large as it's been. There we go. So 0 squared plus 1 squared, this is still 1. So when I go to do the sine of 90 degrees, sine is y value over r. So y is 1, r is 1. So sine is 1. Cosine of 90 degrees. This is going to be x over r, which is 0 over r, which is 0. Tangent of 90 degrees is y over x. So the y is 1, the x is 0. So we're in this situation again where tangent of 90 degrees is undefined. For the others, we have cosecant would be 1, secant would be undefined, and then cotangent would be 0. So you can verify those for yourself, but that's what's going to work out. In the angle measure 180 degrees, at this point, I think you've got the idea of what's happening, but just to show you, when theta is 180 degrees, that's a quadrantal angle because it lies on an axis. A point that you can use here on the terminal side would be -1 on the x, 0 on the y. And you can try and fill out what those values are going to be. And then for 270 degrees, your terminal side, your initial side would still be along the positive x. Your terminal side would be this way. So this is 270 degrees. A point along this terminal side, 0, -1. And then you can use the same arguments we used earlier to come up with the remaining ones. After that, we don't use theta equals 360 degrees because that equals the same thing. It's coterminal with 0 degrees, so it's the same result. So most of the questions you have will say to answer with angles between 0 inclusive and 360 not inclusive, because 0 and 360 are the same. Now, if you want to check yourself, here's a nice little table of all the different trig functions evaluated at each of the quadrantal angles. And so you can kind of get an idea of what those values should be. If you're ever confused on them, the best thing to do, just find a point that exists on the terminal side of the angle you want, and then use the rules that you know of sine, cosine, tangent, and so forth to come up with those values. Personally, I'm not very good at memorizing a whole bunch of numbers associated with a bunch of other numbers. I'm much better at remembering processes and how to develop things. So, take it as you will personally. There's some notations that are different in trigonometry that I want to point out. And that is the notation when you have something squared. So if you'll notice, if you're trying to square a trig function, we have a special notation to just put the square in between the function and the angle measure, just to make it a little bit more shorter to read. So keep that in mind. So if you ever see that, it could be sine cubed theta, cosine to the fourth theta, tangent to the 3/5, whatever. That's just the notation we use for powers. Likewise, there's an unfortunate situation where we have a notation that is sine to the -1. But using what we just talked about, you would think that sine to the -1 theta would be like sine of theta to the -1 power, which would be 1 over sine theta. But unfortunately, that's not what we do. That's not the case. This is a different notation. This sine to the -1 power, it stands for arc sine of theta. And basically what it does is it returns an angle measure based off of a ratio of sides. So it's a completely different notation altogether. And in fact, when using the arcsine function, the return is an angle measure, so it's generally not used as theta as the input. I just did it just because I want you to see how this notation can be confusing. But you'll see it enough in this class that I think you'll just be able to get used to it. Now, identities. We're going to have a lot of identities in trig class, and we're starting with a few today. So the first that we're going to begin with, called reciprocal identities. So basically, we've seen this already. We know that cosecant of theta is just 1 over sine theta. That's a reciprocal identity. Most people don't really need to know that as a formula, but just kind of remember how sine and cosecant are related to one another. The reverse is true as well. If you take 1 over cosecant, the result is sine. Cosine and secant are related in the same way, and cotangent and tangent have the same reciprocal relationship. Quotient identities. It is also true that tangent of theta is equal to sine theta over cosine theta. Now this one isn't quite as obvious, but I can show you very quickly how that works. So sine of theta is equal to, well, let me write it this way, sine theta over cosine theta. Sine of theta, we learned, is y divided by r. And cosine theta is defined as x over r. This becomes a compound fraction, which we never divide fractions, we just multiply by the inverse. So I'm going to invert the denominator, multiply. Well, the r's cancel out, and now I'm left with y over x. Y over x was our definition of tangent theta. So it is true, tangent theta is just sine divided by cosine. As well, cotangent is just cosine over sine. Pythagorean identities. Of all the identities you're going to learn in this class, this is probably the one that you'll use the most going forward into later courses, which is good because it's really the easiest one to remember. Sine squared theta plus cosine squared theta is equal to 1. Well, why is it true? Let's take a look at that. So let's say, for instance, we know the relationship between x, y, and r. So for instance, if I have x squared plus y squared equals r squared. All right, that's how we defined r. Now, if I divide everything through by r squared, all right, let me put that more in the middle, then what happens is I get x squared over r squared plus y squared over r squared equals r squared over r squared. So x squared over r squared is the same thing as cosine squared. So x over r is cosine. Y over r is sine, so y squared over r squared is sine squared theta. R divided by r is 1, so r squared over r squared is still 1. And that's where the Pythagorean identity comes from. We also have two others. And these were a little bit more difficult to remember. And honestly, I still to this day have trouble remembering how they're structured. But there is a way, if you get stuck, to figure this out. So for instance, let's say I have the one that everyone remembers. If I know this one, I can figure out the rest of them. So if I go through and divide everything through by cosine squared, then what happens is I get sine squared theta over cosine squared theta plus cosine squared theta over cosine squared theta equals 1 over cosine squared theta. Let me scroll down just a little bit. And what happens there is sine over cosine, we know that to be tangent. We just developed that. And in particular, this will be tangent squared since both are squared. Cosine over cosine is 1. 1 over cosine, we've learned, is secant. So this is secant squared theta. So if you're ever unsure of how these are structured, then just remember that little detail. It works for the other one as well. So for instance, if I start with sine squared theta plus cosine squared theta equals 1, and divide everything through by sine squared, the other one, then what happens is I get sine squared over sine squared is 1, cosine over sine is cotangent squared, 1 over sine squared is cosecant squared. So it's easy to get the other two if you remember the first one. So we're going to see a few problems of how these are used. First off, says to find secant theta if cosine theta equals 3/5. Well, recall secant theta and cosine are inverses. So if I want to find secant theta and cosine I know is equal to 3/5, then secant's going to be 1 over 3/5, which is 5/3. All right, next example, identify the quadrant or quadrants of the angle theta that satisfies sine of theta is greater than 0 and cosecant of theta is greater than 0. So to do this, you just need the idea of where your sine and cosine, tangent, those trig functions are positive and negative. So remember, all students take calculus. So all sine, tangent, cosine. So if sine is positive, we could be in quadrant 2, but we could also be in quadrant 1 because sine's also positive there. Cosecant is just the inverse of sine, so it would kind of follow the same pattern. So this would be quadrant 1 or 2. All right, where cosine is less than 0 and sine is less than 0. So all students take calculus. So if cosine is less than 0, we can't be in quadrant 1. Sine is less than 0, we can't be in quadrant 2. Cosine and sine are both negative in 3, but cosine is less than 0, we can't be in quadrant 4. So in this case, quadrant 3 is our only possibility. And that's really how you answer any of those kind of questions. C, find cosine theta given that sine theta equals -4/5 and lies in quadrant 3. I'm going to draw a little sketch here. All right, so my angle measure is in quadrant 3. So I'm just going to draw an angle in quadrant 3. Now, I'm going to make a right triangle with respect to the x-axis. And that's basically the theta that I'm going to work with. That's basically the angle that I'm going to work with. So this is my observed angle. I'm going to call it alpha for right now. And if sine is -4/5, sine is that relationship of opposite over hypotenuse. So I know those two sides of the triangle. If I want to figure out what cosine is, I need to figure out x. Well, I could use the Pythagorean theorem and say -4 squared plus x squared equals 5 squared. So 16 plus x squared equals 25, or x squared equals 9, so that x is either positive or -3. It just kind of depends on the quadrant that I'm in. So being in quadrant 3, x has to be less than 0, so -3. So cosine of this angle measure is going to be -3/5. That's one way. Another way is just using the Pythagorean identity. So if cosine squared theta plus sine squared theta, which we know to be 4/5, equal to 1, let's see how this works out. So cosine squared theta, plus 16 over 25 equals 1, which I'm going to write as 25 over 25, just because I'm going to have to combine like terms. So I'm going to subtract this fraction from both sides. So cosine squared theta is equal to -16 over 25. Oh, I'm sorry. I meant to subtract the 16, not just write it down. So 25 minus 16 would be 9 over 25. So that cosine of theta, when I take the square root of both sides, would be plus or minus 3/5. It's got to be one or the other. So we just choose the sign based off the quadrant we're in. And again, in quadrant 3, cosine is negative, so we would throw out the positive there, and cosine would be -3/5. Find the values of the 5 remaining trig functions if tangent theta equals -3/2 and theta is in quadrant 2. Okay, I'm going to draw an angle in quadrant 2, just to begin there. Trig is a very applications-rich mathematics. So that means you can almost always draw a diagram of what you're doing, and that will almost always help you out. All right, so I have an angle measure in quadrant 2. So here's theta. But when I drop this triangle to the x-axis, I kind of am working with this observed angle right here, okay? So tangent theta, it's going to be wait. -3/2. Well, wait a second. You might think that's a little bit weird. And I would agree with you. And the reason that's weird is because in this case, the y value needs to be positive and the x needs to be negative. And that's actually okay. So when you have a fraction like this, you're not necessarily being told that the numerator is negative. You're being told that the value of the fraction is negative. So you could write -3/2, or you could write -3/2, or you could write 3/2. These all mean the same thing. So what that tells me is I have to pay attention to my signs, because trigonometric functions don't necessarily affix your signs for you. You have to be aware of them. So I need to make a fix there. All right, that works out. Now, the remaining trig functions, in order to get them, I'm going to need to know the value of r, so the distance from the origin. So r is going to be the square root of x squared plus y squared, and I actually swapped those, but that's okay because they're getting added together. So this would be 9 plus 4, which is the square root of 13. So this distance along here is the square root of 13. So I don't know what the angle measure is, but I know the sine of that angle measure, whatever it happens to be, is going to be the opposite side over the hypotenuse, which is 3 over the square root of 13. And this is, I need to change this so that I don't have a rational in the, or I'm sorry, a radical in the denominator. So I just need to multiply by the square root of 13 over itself. So 3 square root of 13 over 13. All right, cosine theta. Cosine is the adjacent side over the hypotenuse. So the adjacent side of this triangle from my observed angle is -2 over root 13. And I'm going to have to do the same thing to rationalize here. So -2 root 13 over square root of 13 times square root of 13 is just 13. All right, I've already got tangent. So I can get cosecant next. And I don't really need to do a lot of work for cosecant. I'm just inverting sine, but I'm going to invert this form right here, because when I invert, I'll have root 13 over 3, which means, you know, the rational is in the, the radical is in the denominator. And so I don't need to rationalize. All right, then secant in a similar fashion is going to be square root of 13 divided by -2, but it's more common here to put the negative in the numerator. So negative root 13 over 2. Then the last one is going to be cotangent. And since I already had tangent, this is just the inverse of that. So in this case, -2/3. So there's a lot covered in this video. There's going to be a lot covered in the next video as well. We'll bring it all together before we get to the end of, at least to the end of chapter 6. There's a lot of trigonometry thrown at you. The most important takeaways, though, are these mnemonics that tell you the relationship between the sides of a triangle for cosine and sine, so SOHCAHTOA, and the mnemonic for the signs of your trigonometric functions in each of the 4 quadrants. So all students take calculus. So those mnemonics, go going forward are going to get used a lot. You want to make sure you know those. And then not trying to say that anything else is any less important, but going forward, those tend to be the things that you use the most when you're solving equations.